I would like to tell about first-order mean-field type control problems and the so-called lattice approximations that leads to some control of error bound here. And first of all, what is about mean-field type control problem? Now we have a control problem in the space of probability measures with the dynamics given by the continuity equation, where U depends on the current state or probably on some label of agent, when the purpose of our control is to minimize the quantity G depending on the flow of probabilities at the last time instant M of t here. And this formal control problem appears as a mathematical model of the control of system consisting of infinitely many similar agents. Those interacts via some external media. And we assume now that the dynamics of each agent is given by ordinary differential equation that is on the slide. And the main feature of this differential equation is that, that now dynamics depends not only on the state of each agent, his or her control, but also on the distribution of all agents. This situation also appears in the mean field game theory. But now we have a very important difference with the mean field game theory. Now all agents are governed by some one decision maker who tries to optimize the terminal payoff that is given by G of M of t. I will repeat it once more time. And M of t is now a probability on the phase space that describes the distribution of all agents and time t. And due to the first order deterministic nature of our system, we can assume that M of t of y is a fraction of agents who are in the set y at time t here. And within this problem, we have some questions. First of all, whether there exists an optimal control. What is about characterization of optimal control? What about Van maximum principle? What about dynamic programming? And the mean field type control problems. Search another problem about finite state approximation, because now we have infinite dimensional problem and we wish to find some finite dimensional approximation. And I will talk about two points in my talk. First, it's about existence of optimal control in the mean field type control problem. And the second is finite dimensional approximation that is given due to the method that is called lattice approximation. And if you wish to ask me, please be free to interrupt me. And the plan of my talk is the following. First, I will talk about some basic notation. Then I will spend some time talking about relaxation of finite dimensional control problem, the control of each agent. Then I give a formalization of dynamics of the first order midfield type control system. Then I will turn to the approximative systems, and approximation will be given by with the help of so-called mean field type Markov chains. And I will give a very short introduction to the mean field type Markov chains. And then I present main example, that is approximation theorem, main result, that is approximation theorem. And I would like to complete my presentation with a very simple example how we can construct an approximating Markov chain acting on a regular lattice. First, I will use the lattice symbol to for Pash-Ford operation, and it is defined as follows. If we have two measurable spaces, if we have a probability on one space and a measurable function from one measurable space to another, then we can transfer a measure M from sigma 1 to sigma 2 by this rule. Then I will consider a metric spaces. We will consider only Borel probabilities on a metric space. We denote the space of all probabilities on X by P of X, and denote the space of probabilities with the finite path moment by PP of X. And it is well known that the space of probabilities with finite path model can be metricized using so-called Watershed distance. And the idea of Watershed distance is the following. The path power of Watershed distance is equal to the value of optimal transportation problem with the cost given by path power of distance between 2 points. And here, this formal definition means that we have a set of plans between M1 and M2, and we compute the cost of our transportation according to the given plan pi, and then we minimize this cost, and this is the path power of the path Watershed distance. Then, to simplify my construction, I will consider that the phase space for each agent is d-dimensional torus. And the idea of construction of torus is that we identify the points from RD with the integer distance between them. If the distance on each coordinate is integer, then we identify these 2 points. And with some abuse of notation, I will denote the distance on d-dimensional torus by the norm between of difference x and y. This is a bad notation, but I prefer it. And further, I will also use a short way to say that we consider the set of all trajectories defined on some interval SR and defined it C calligraphical SR. This is the set of all trajectories defined on interval SR. And if we are given with a trajectory, then we can ask what is its value at time t. Et of xt, this is the evaluation operator of the trajectory x dot. And now I complete the presentation of general notation, and I would like to turn to the analysis of dynamics of single agent. And for a while, assume that M of t is given, and we are faced with the dynamics of single agent, of the representative agent, and it is given by ordinary differential equation. And here the question is, what is the set of admissible contracts? A very natural answer to this question is to consider measurable controls of the representative control agent. But here we have some problems. First, what is topology on the set of measurable controls? What about compactness of the set of trajectories? Those are generated by measurable contours. What is about existence of the optimal contour? And we have very old and well-known example saying that if we admit only measurable contours, we have no compactness, and therefore we have no existence of optimal contour for the single agent. And this example is very simple. We have dynamics, we have vectorgram given by this half circle, upper half circle. And we assume that in the initial time, we are placed at the 0, the origin, and we wish to stay in the origin for some time, say OT. And if we use only measurable contour, we cannot stay in the region. We will move, probably we will have a very small moves, but we will move. This is due to the fact that we should use either, if we have any control except 0, pi, we will move upward. And if we use 0 and pi, we will move only either rightward or in the right direction or in the left direction. And we will have some oscillation here, in any case. And the idea is to use so-called relaxed controls. We will say that a function from our time interval to some set of probability measures is called weakly measurable, is if for any test function phi, the mapping t assigned to t, the integral of phi x ct dx is measurable. Then we consider the set of all weakly measurable function psi, and we any such weakly measurable function taking values in the set of probability measures over our control space U is called a relaxed control. And from this time, I will denote the set of all relaxed control by U calligraphical. And here we can define a topology on the set of relaxed controls given this topology is generated by narrow convergence on the product of Lebesgue measure and our weakly measurable functions psi n. And what is very important here is the fact that if you consider this topology generated by product of Lebesgue measure and our relaxed controls, then the set of relaxed controls is compact if the set of original set of control space is compact. And if we are given with the relaxed control psi, we can define a trajectory by this way. So in each time instant, we integrate the right-hand side according to our distribution of controls psi t. And we have that the set of relaxed controls is compact. There exists an optimal relaxed control now. And what is a very great effect here, that the set of measurable controls is dense in the set of relaxed controls. And in this very simple example, we can compute that optimal control is to share our control between 2 points, 0 and pi. This is in this example. Here we should put half of our forces and pi and half of our forces in 0, and we will set here in the region. Now, let me come back to the mean field type control problem. Here we have the dynamics given by continuity equation and payoff functional given by g of m of t, and now m is a distribution of agents at time t, m of t. And I would like to recall that, in fact, we consider the system consisting of infinitely many agents. And I would like to give a formalization of this problem starting from this point, starting from the idea that we have a system of infinitely many similar agents. And from now, I assume that U is a compact. All functions f and g are continuous, and f, that is the dynamics, is continuous with respect to x and m. And if we are given with the distribution of agents, and for now is, for a while, it is an external parameter, relaxed control, and time instant s, then we can define the motion of sampling agent by this rule that is given by original differential equation when we integrate our space of our controls according to the measure xi. And what is here very important, that we now can define the operator that assigns to initial position of sampling agent y and the control xi a whole trajectory, and we denote this operator by traj, as r is now for time interval, and m is an external parameter that is distribution of agents. Then, what is now the control of the whole system? We know what is the control for each agent, but what is a control for the whole system? And the idea here is the following. We assume that our decision maker assigns to each agent its control, but we have infinitely many agents now. And we will assign not an individual control, but a distribution of controls. And we assume that now a control is a pair, is a distribution on phase space, that is now d-dimensional torus, and a space of probability of relaxed contours u, such that if we project our distribution alpha on the phase space, we will get m. And the idea is the following. We now, if we disintegrate alpha with respect to m, we will have some cloud, some distribution of measures psi. And the idea is that if the agent is at the initial time s placed in the space, the point y, he will get her control according to the distribution alpha of x, that is disintegration. And this is the idea of our distribution of controls. And now we assume that we are given with the time interval, and we are given with initial distribution of agents, and we are given with some distribution of controls that is admissible at m star. And we say that m of t, that is a flow of probabilities, is generated by these parameters if we can find a distribution on the set of trajectories high, such that first we start from m star, this is initial position condition, then m of t is equal to the evaluation of measure high by the operator et, by this evaluation operator, and then high is produced as push forward of the measure alpha by the operator that assigns to each initial point relaxed control the whole trajectory. So we have some fixed point, and the idea is, I think, rather natural. It says that we wish to have some distribution of motions such that at each time m of t is equal to its evaluation. So we have some projections each time. And if we put m at the dynamics of each agent, then we will get the distribution of trajectories high. And so this is some picture trying to explain what is the main idea of this definition. We have now some distribution of agents, and then we assume that each agent now is produced in the assumption that the dynamics of all agents is equal to m of t, and then we try to compute the real distribution of agents and time t. And using the fixed point theorem, one can find that at least one, that given alpha, we have one corresponding set flow of probability measures. And we have another equivalent formulation due to Jimenez, Marigonda, and Quincampoix. And it says that the flow of probabilities M is generated by S initial time, initial distribution of agent, and initial and some admissible distribution of contrast alpha, if one can find a velocity field V t of x such that first V t of x lies in the convex hull of our vectorgram, and if we put V in the continuity equation, that is velocity now, we will have that a continuity equation holds in the sense of distributions. And now I think that I tried to explain what is the motion in the mean field type control system, and what is now the optimization problem here. And the idea is the following. We assume that we are given with initial time, say TO, the initial distribution of agents, MO, and we wish to find a distribution of controls alpha that minimize G at M. Now we put T for the terminal time, and that is the parameters. And using the compactness arguments, one can prove that there exists at least one solution of the mean field type optimal control problem. It's a very standard theorem here. And since we have the solution of optimal control problem, we have a value function. Value function depends now on initial time and initial distribution of agents, that is a measure. Well, here that is equal to the G or at the optimal distribution of controls. And the main problem here is how we can compute this value function, and can we find also a optimal distribution of controls, or near optimal distribution of controls. And certainly we can write here a Hamilton-Jacobi-Bellman equation that is an equation in the space of probability measures. And we will face with a lot of issues about what is now the derivative in the space of probability measures. But now this question is near to be solved. But okay, we will have Hamilton-Jacobi-Bellman equation, and we can define here the viscosity solution. Okay, we will have existence of uniqueness theorem. What's more, it gives nothing to the question how we can compute the value function. And another way here is to use some approximation. And a most natural approximation is so-called finite agent approximation. And we assume that we consider now not the system of infinitely many agents, but we consider the system of n agents. And then we replace our dynamics, assuming that on ith agents, only other agents will influence here. Then we can replace the state of the system as an empirical measure. And it's a very nice result here that the solution of optimal control problem for the n-agent game, n-agent control problem, converge, but up to subsequence, to the solution of the mean field type control problem. There are two approaches. First is the result by Lacker. He used the optimal control arguments here, and another is the recent paper by Ganboma, York, and Zweig, who used this Hamilton-Jacobi-Bellman arguments here. And I would like to emphasize that these results are very important for this theory. In fact, our theory is consistent. It really approximates the finite agent system. But now we have, but it gives nothing also to the problem how we can compute the value function, because we have no approximation rates. And another way is to replace the dynamics of each agent with some kind of dynamics defined on lattice. And here we will consider the case when the dynamics of each agent now is determined by Markov chain. And to have, I think that's a good picture. The following: we discretize our d-dimensional tokens by some lattice, probably it is regular lattice, and each agent now can jump from one side to another. And we will have in the following, that the dynamics of distribution of all agents is now given by ordinary differential equation. And this will lead to the finite-dimensional approximation of our control problem. Probably there are some questions. Or no? Okay.
So the lattice approximation is for the state space, for the control, or
for the state space.
I see. Thank you.
It will be no approximation of control space, no approximation of time, only approximation of control space.
State space. Actually.
Oh, state space. Sorry. Okay.
Thank you.
And some formal things. I will consider now the system with dynamics given by Markov chain. What is Markov chain? I will consider only finite state Markov chain, and I consider that we are given with some finite set, say S, and I will assume that S is a subset of our d-dimensional torus, and on the set S, I will consider a simplex defined on the numbers. We have cardinality of S, and I will consider simplex sigma that consists of all sequences mu indexed by sides from S, and each element of mu is non-negative, and the sum of mu is equal to 1. So we have a real simplex here. And one can notice that we have poor states, the case when we have all probability concentrated at one side. And here, you see that S now is a subset of our d-dimensional torus. And we can consider not only simplex S, but also a simplex of probability measures over the S. And I would like to compare these two objects here because I will operate both. First, S sigma is a subset of R in the cardinality S. This is wrong S here. And if we are given with the two sequences from our sigma, mu and mu1 and mu2, we can compute the distance using the path distance on the finite dimensional space. I will denote it by mu1 minus mu2p, but this is a distance on our simplex sigma. And we have an isomorphism between sigma and the set of probabilities over S. If we have a sequence mu, then mu child is the empirical measure obtained by the following rule. We put a mass of the weight mu x bar, where x bar is a site of S, at the site x bar here. And this is isomorphism between sigma and PS. But this is only isomorphism. It does not preserve distances. And we have the following comparison result between the distances on sigma and on the set of probabilities on S. One can find two constants, C1 and C2. They depend on S certainly, such that the distance coming from finite dimensional space is controlled by C1 multiplied by the Watershed distance, path Watershed distance, but the path Watershed distance between the lifted sequences mu1 and mu2 is not greater than C2 multiplied by path distance, finite dimensional distance, in the power 1 divided by 2. And state space and space of distributions. What is biodynamics? We assume that the dynamics is given by continuous time Markov chain. This means that on some short-term interval, our agent can jump from the site x bar to the site y bar with the transition probability that is equal to q x bar y bar time t multiplied by delta t plus some small thing, and the conditional probability of remaining at x bar is equal to 1 plus q x time t multiplied by the distance of our time interval. And here we assume that q x y is non-negative for x non-equal to y, when the sum on the row of this matrix is equal to 0. That is formally written in this row here. Okay, and now if the probability of being at time at site x bar is equal to mu x bar t, then we have a sequence that describes the distribution of probabilities, and this sequence is an element of our simplex sigma, and we have the Kolmogorov equation that is now ordinary differential equation for the dynamics, or we can write it in the system of ordinary differential equation, or we can write it in the vector form. And I would like to emphasize that for this very simple system, the dynamics of distribution of agents is a finite dimensional system, but the dimension of our problem is equal to the cardinality of S here. Next thing, next step is due to Professor Kolokholtsov. It is to assume that the transition rates depends on current distribution of agents. We'll write here that now our Kolmogorov matrix depends not only on time, but also on mu, that is a distribution of agents. But for this case, we also can write the Kolmogorov equation, but now it's nonlinear. Okay, next step is to add control. And now we consider the system where we have one decision maker who controls infinitely many agents, infinitely many similar agents. And what is now the state of the whole system? The state of whole system is given by distribution of agents, that is a sequence mu lying in our simplic sign. And each agent is governed by our Markov chain with the Kolmogorov matrix. Now it depends on time, current distribution of agents, and current control. And we assume that the decision maker tries to minimize the quantity equal to G hat mu of t, but I assume that our G hat is equal to G at the lifting of mu at the last time instant. There is the precise formula. What is G hat now? We assume that we are given by the function G, that is the payoff functional from the original problem, because I would like to approximate the original problem by the control Markov chain. And then I will consider this a bit specific functional. And what we have now? Now we have that the dynamics of the our system, or the distribution of agents here, is given by nonlinear controlled Kolmogorov equation. And this is usual finite-dimensional system. But here I need to say something more. What is control here? And I will consider, there are some conditions of Q, probably I skip them. And I will consider so-called feedback controls. That means that each agent uses the control that depends on time and depends on the site where he is at time S. And additionally, I will consider relaxation of space of controls. That means that at the time t and at the site x, we assume that the set of instantaneous control is now equal to the set of probability measures over u, that is u instant here. And we consider a sequence of measures, that is gamma s, indexed by site s from S capital, and that u instant in the power s is now the set of instantaneous contours. And the idea is the following. We assume that at the time t, at the state x, our agent who is at the state x will share his or her control according to this distribution of controls. Then we rewrite our transition probabilities. Now we have Q calligraphical here, given by this formula. And then we have Kolmogorov matrix by this formula. And now we have some huge space of controls that each control now some sequence of distributions. But the dynamics of the whole system is still finite-dimensional, given by this formula, and we have a usual problem of minimization of some quantity given by G hat of mu of t. This is a finite dimensional control problem. Probably we have now a huge control space, we have now a huge dimension, but this is a finite dimensional control problem. And we can treat it as a finite dimensional control problem. Let's do it. We can compute a Hamiltonian, we can write down the Hamilton-Jacobi equation, and it is well known that the solution of the Hamilton-Jacobi equation is the value function of our finite dimensional control problem. And there is a formal definition of solution. We have super solutions by this formula. We have sub-solutions, and if a function is a sub or super solution simultaneously, it is called a viscosity super solution here. And now I need one more definition due to a very poor phase space, because now I would like to present the what is approximation of our control problem, and I need some subtraction operator on torus. But I cannot subtract on torus because torus is not a linear space. And I introduced some, some replacement of this operator that is denoted by L, and L is a function that assigns to a pair x, y, a vector z, that is a usual d-dimensional vector, lying in the x minus y. I'm to recall that x minus y is the subtraction of two sets, because an element of torus is a set, and we now have some set of vectors, and I would like to assign to this set x minus y an element of minimal norm. This is the idea of subtraction here. And we say that our lattice S and our Markov chain are so that first, our lattice S approximate our d-dimensional torus in the way such that the maximal distance between an element of torus and an element of our lattice is not greater than epsilon. Then the next condition says that if I am given with the dynamics f that comes from the original problem, and I compute the average jump according to the Markov chain, then the distance between them is not greater than epsilon. And the last condition says that our Markov chain is really, in some case, near deterministic. That says that its variation is not greater than epsilon squared. And under these conditions, I will prove the main result. To introduce it, I need one more definition, and I think that will be the last definition of my presentation. It says that if we are given with the probability M, that is a probability over torus, then we denote by projection of M over S a nearest element of our simplex S. That says that we will have now a function that assigns to a sequence mu the distance between its lifting to the set of probability measures and M, and I will minimize this distance as says that the sequence that minimizes this function is a projection of M over set S, of the lattice S. Okay, I was wrong. I need one more definition. We assume that the modulus of continuity that is always well defined according to the fact that G is continuous while torus is compact is denoted by sigma G here, and we will have some constant that is precisely computed. And we assume that if there is a solution of the Hamilton-Jacobi equation for the mean field type Markov control problem, that is a finite dimensional control problem here, then for any initial time and any initial distribution of agents, value of our initial control problem can be approximated by the value of phi with the precision not greater than sigma G, that is modulus of continuity of our payoff function, at some constant multiplied by epsilon. So if we have Lipschitz payoff, we will have a linear approximation here. And then if the stronger result, if we're given with the super solution of our Hamilton-Jacobi equation, then we can construct a distribution of controls that gives this approximation here. If we can construct distribution of controls alpha such that if M is generated by this alpha, then the payoff on this trajectory of this flow of probabilities is not greater than the value of phi, that is our value function in the approximative problem, plus some approximation error that is computed precisely. Okay, and here I tried to write down how we can compute our suboptimal control, but I think that it's better to skip it. And I will turn to the last part of my presentation, that is about lattice Markov chain defined on the regular lattice. And we assume that we are given by some h such that its inverse is natural. And we define as h to be equal to h multiplied by set of integers in this power d intersect with d-dimensional torus. So we have now regular lattice with the step equal to h. And then we can write our dynamics in the coordinate-wise form. And let EI stand for the ith coordinate vector. And we have a very natural idea of construction of approximative Markov chain. We say that assume that our agent is at time t at the site x bar. Then he will jump to the neighbor lattice y with the probability equal to 1 divided by h on the absolute value of fi. So he will write up with the probability f2 if y is positive, and he will write down if f2 is negative, and the same for the x. Jump right if f1 is positive, and he can jump if f1 is negative. And this defines our Markov chain here. And if we additionally assume that our dynamics is Lipschitz continuous with respect to first Watershed distance, then we can compute the distance between here we can compute and we can do function. It's nice approximation of the value function. And I am in the conclusion. I would like to say first that I can, in my presentation today, I considered on the case when we have a mean field type control problem. We can consider also the case of two-person zero-sum mean field type differential games. And this is written in my paper that now is published in Snowdare, but there are a lot of technical details, so I prefer to skip some technical details. And what is about how we can use these results? First, we need numerical methods, and certainly we have some course of dimensionality here, according to the fact that the precision of accuracy of approximation depends on the number of sites, but I think that it's a good way to produce numerical methods for mean field type control problems. Then we wish to extend our result and estimate the distance between tubes of trajectories, and I probably will do this soon. And the next question here is, can we give approximation by more general systems, probably by the general Levy-Hitchin processes? That is all. Thank you for your attention.